So now let me just cut to the chase then. The awful truth about zero G, there's no such thing. It does not exist, except as a really neat term. I use it in writing, but as actual physics, it doesn't. Yeah, for laughing, LOL, or crying out loud. So the next question I would expect that a lot of people would ask is, as the transmissions inside your brain start to freeze up, why are the astronauts floating around in space? And this is hapless Harry, the crash test astronaut. We use him a lot in our zero G demonstration activities. Hapless Harry, he's got a pretty good health plan. He's already had 2 knee replacements, courtesy of my daughter. He takes a bashing, keeps coming back for more. Okay, so why do the astronauts float around in space? What causes that? So just go ahead and type a few answers in there, please. Yeah, because part of what I'd like to learn is what you understand, because that helps us in teaching. Okay, so Anthony says free fall, minuscule gravity. There was a previous one that I missed. It just went by real fast. Gravity. Okay, yes. Actually, the reason the astronauts are floating in space is not because there's no gravity, but because there is. And the answer, free fall, is correct. Sorry, Harry. The answer, free fall, is correct. That is what's going on with the astronauts. And what I want to do is talk a little bit about how we discovered it. And when the time comes, as I get a little further down into this, Dave, am I able to switch my screen to run some videos that I've got on my iPad?
Yes, you should be able to, screen share that.
Okay, good. Yeah, because I don't have the full demonstration unit set up in here because I don't have the electromagnet to do the drop tower. And this way, we just a little bit faster. Okay, it is called zero G because zero gravity. Okay, that is the popular understanding. That's what a lot of people think. Okay, so here's my question to you. If it's zero gravity, if there's no gravity in space, what keeps space station in orbit around Earth? What keeps the moon orbiting around Earth? What keeps Earth in orbit around the sun, etc.? If there's no gravity in space, why don't we just go flying away? Mass. Okay, yeah, everything has mass, but if there's no okay, yes, because there is gravity. So what's going on, and what I'm going to talk a little bit about, is how we discovered gravity, how really how our understanding of gravity grew. Everybody knew that something pulled us down, but there was a lot of misunderstanding. And for a long time, really over 1,500 years, everybody followed the teachings of Aristotle, that a heavy object would fall faster than a lighter object because it had a greater desire to return to the Earth. Sound a little bit like baloney to you? Yeah, so the problem was nobody looked critically at it until Galileo. And what did he do? Early 1600s, what did Galileo do? Okay, he did not invent the telescope. A lot of people think he invented the telescope. What he did was reinvent the telescope. He made a better one. He read a description, built his own, made a better one, invented modern observational astronomy. He also started inventing modern physics. And one of the most famous things that he's known for is actually something he didn't do. Let me get over here behind the table. It's something that he didn't actually do. And so, by the way, this is the first time broadcasting from my newly done work cave here at home. So one of the things that he's famous for, something he didn't do, which was dropping 2 cannonballs off the Leaning Tower of Pisa. Now, he had done experiments with cannonballs rolling down ramps. And really got started looking at a pendulum, keep an eye on the time, watching a pendulum, a chandelier in a church, and noticing that the period, the length, the time that it took to swing back and forth did not depend on how heavy the pendulum was, how heavy the chandelier was. So he did experiments with cannonballs rolling down hills, and he determined that everything is attracted equally to Earth. So he said, if you went on top of the Tower of Pisa and dropped 2 cannonballs and I'm too far away to read the answers. Which one is going to hit the ground first? And a lot of people will say the big one, because yeah, if I drop them center to center, the big one has a bit of a running start there. But they arrive at the same time because they are attracted equally to Earth. And this was a big change in mindset in physics, that things were attracted equally. He allowed, yes, for air resistance. So if I drop the feather, the cannonball is going to arrive a little bit before the feather arrives because of air resistance. So he said, yeah, there's a little bit of air resistance. You get rid of that somehow, and the cannonballs will arrive at the same time. They'll hit the ground at the same instant because they are attracted equally to Earth. Okay, so we fast forward about half a century to Sir Isaac Newton, and he invented something that bedeviled me and turned me into a writer instead of an engineer. He invented calculus. Found that I couldn't quite do the equations, but I could do the words, so I became a writer and now an educator. So I don't design the spaceship, but I can tell you how it's designed, which is an important job. So Newton said, yes, things are attracted equally to Earth, and he was famous for not an experiment that he did, but an observation that he saw an apple. He was out at his mother's place out in the countryside because the Black Plague was just ravaging London. So he left Cambridge University and he's out in the countryside at his mother's place, and he'd been puzzling over why the moon doesn't fall to Earth. And when he saw an apple fall from a tree and hit the ground, the light bulb, of course they didn't exist then, but the light went on, and he realized that gravity attracts the apple to the ground, but all matter, all mass produces gravity. So the atoms, the mass in your bodies produce gravity. And what he calculated was it goes on forever. It never stops. It goes on forever and ever. So someone has said weak gravity, reduced gravity. Yes, that's true. At the altitude of space station, you only weigh about 94% as much as you do here on Earth because of gravity, but you're actually in free fall. But if you weren't, you would be 94%. But that's still enough to hold space station in orbit. And what he determined was that what keeps the moon in orbit around Earth was here. Okay, so here's the Earth and here's moon. What kept it in orbit was this delicate balance, this ballet, if you will, where the moon has outward velocity, but Earth's gravity is pulling it in. And when you balance the two, you get a curved path that goes around and around and around the world constantly. Now, there are a lot of other subtle factors involved, but we'll go into them right now because, the moon is just slowly, millimeter by millimeter, moving away from Earth, and they measure that with a telescope not too far from here. So Galileo says objects are attracted equally to Earth. Newton says yes, but Earth is attracted to objects. So there was a real famous demonstration done by astronaut Dave Scott on Apollo 15 almost 50 years ago. In fact, this will be the 50th anniversary. I believe it's in April. So standing on the surface of the moon, he held a hammer and a feather. It was a feather from a falcon. I believe it was the Air Force Academy mascot. Feather and a hammer, and talked about Galileo and his experiment dropping cannonballs. So when he dropped them on the moon, which one do you think arrived first? Which one hit the ground first? So I'm close enough. I can read some of the responses. What's going to hit the ground first? So I've got the hammer. Okay. Anybody else? Why the hammer? Why is the hammer going to hit the ground first? Okay, they're going, and Hunter says they're going to hit at the same time. Let me get my glasses out here. Same. Okay. So probably a fairly good guess that here in my studio, Yeah, the hammer hits first. But when Dave Scott did it on Apollo 15, the hammer and the feather arrived at the same time. Now, here's the part that's going to fry your brains. When the moon's gravity was pulling the feather down, gravity from the feather was pulling the moon up. You ever consider that one? You ever think about that? I mean, just right now, gravity from the feather is pulling on Earth, and as the feather falls, it's pulling Earth upward. Not very much. You'd probably burn out a supercomputer trying to calculate a number that small, but it's real. So gravity drops off very, very slowly. So if you went to an altitude of 4,000 miles, 1 Earth radius, gravity would be 1/4 as strong as it is here. Go out to 3 Earth radii, or let's make it even bigger, to a distance of 10 Earth radii from the center of Earth, it'll be 1/100th, 10 times 10, it drops off by the square, 1% as strong. Go out to 1,000 Earth radii, which would be 6 million miles away, it would be less than 1/1,000,000th as strong as it is here. So you sort of get the idea. It's going to get weaker and weaker and weaker, but it's never going to hit zero. So that's why zero gravity is not real. It's a great term. I use it all the time when I write. It's a wonderful expression. You say 0 G, wow, everybody knows, but it's not real physics. It's not really what's happening. So, okay, so Galileo says objects attracted equally to Earth, and Newton says yes, objects attracted equally to Earth, but Earth attracted equally to objects, because for every action there is what? For every action there is opposite and equal reaction. So you push on something, it's pushing back. Gravity is pressing you down into Earth, and Earth is resisting with the equal amount of force upward. Otherwise, we just sink to the core and we wouldn't be here. Okay, so now along comes Albert Einstein. And Albert does what I like to call the Einstein's evil elevator experiment. He says, yes, objects attracted equally to Earth, Earth attracted equally to objects, all objects attracted to each other. But if you put a man in an elevator, close the doors, close the doors, and you cut the cable for the last second or two of his life, he cannot tell if he is falling to his doom or the force of gravity has been magically turned off. The two effects are equivalence. That's called Einstein's equivalence principle. That's what's happening to the astronauts on board space station. They and the space station are orbiting Earth forever together, falling and never hitting bottom. So free fall is the right description. Free fall is the right description. So how can you experiment with this at home? And as I said, you can do it with a cell phone. And I'm going to run some videos of some experiments that I had done. But first, what I want to do is show you a little bit of the equipment that I've used. And this, yes. Okay, don't really need them now, but I'm just making a little safety pitch. You build something, always wear safety glasses. I mean, in activities in our classes, we have had kids snap plastic picnic knives. So we make them all wear safety glasses. Just protect your eyes, you don't get replacements. Okay, so my demonstration apparatus is this monster here. And the way I've got it set up, I mount the cell phone here so that you can record with a demonstration apparatus you put here. And I just put plastic, you don't have to do it with yours, put plastic on the sides so you get light from the outside. Plus, teachers, if you do this with a class, the kids are going to feel like something magic is happening if they can't see what's inside the box. I mean, you go to a magic show, what are you looking for? You're looking for the trick mirrors, the invisible wires, whatever the magician is using. We want this to be magical, but we don't want the kids to think it's real magic. Okay, we want that sense of wonder. Okay, so what kind of experiments do I do in here? Some of them have been with, and I'll run videos for you, Hapless Harry, the crash test astronaut, the apple falling, little fluid flow toys, and birthday candles. So one of the things that I'll show that we'll come to is we'll wonder, I'm going to ask what happens when a candle goes into free fall. This kind of research is the most important thing that we're doing on board International Space Station, is understanding how fluids, gases, liquids, et cetera, work together, how plants grow, how they change. Most important, what happens to the human body when you're in space? And we're actually finding that zero G, as much fun as it is to float around, zero G is pretty rough on the human body. And we're just now really learning the right questions to ask. So before I go to showing the demonstrations, there was an online question earlier. Where one of you asked, can you move by swimming in space, inside the space station? And the answer is not really very well. And that's simply because the air is too thin and we don't have feathers. In fact, you look at a feather and the design is really to capture the air and work with it. And we just don't have feathers. We have hands, etc. But it's the first natural reaction. I'm very lucky. I got to ride on the NASA zero G plane, and that's the first thing you try to do. 1983, Space Lab 1, 2 astronauts come into the laboratory module on shuttle, and Ulf Merbold from Europe, first time he'd been in space, he's, arms all over the place. And it's almost like he's trying to fly or to swim before he got his sea legs, if you will. Owen Garriott, who had spent 2 months on board Skylab 10 years earlier, came in and he's got his legs tucked under him and he's just very gently grabbing the handrails and moving from one to the other. And I mentioned that to him after the mission, and he said, I didn't even notice that. He readapted right away. Okay, so let's go. Pardon me while I get in here real close here. And let's see, can I go to share screen? Yes. Okay. Okay, it doesn't seem to be letting me do that very well. We've only got about 5 minutes left. Okay, and let me get into camera roll. So where, when you just know it, I spent all that time this morning getting zero G stuff lined up, and now it is hidden from me. So let me try something here. Can you still hear me, Dave? Dave, can you still hear me?
Yes, sir, I am here.
Okay, good. Just wanted to make sure. And let me know if the audio drops out, because I'm going to try to get into my zero G stuff.
Sure.
And is that showing? Or is it just me?
Not yet.
Okay. So let me go back into Zoom, share screen. Okay, start broadcast. Okay, and okay, do you have Apple's Harry there?
Yes, sir, we're good.
Oh, excellent, great. Okay, so Harry and the feather are held up by a magnet. And by the way, magnetism and gravity are two completely different forces. That's an answer I get sometimes. Magnetism holds space station in orbit. Nope, two completely different forces, and they don't interact. So here we go into free fall, and there you got Harry and the feather falling at the same rate, equally attracted. Now I've got to give this poor guy a back brace. Okay, so the next one, got a candle, just a little birthday candle. In fact, I think it's the same one that I just had. So what's going to happen when I put this, that kind of gives it away. So what happens when it goes into free fall is convection is turned off. Because what does hot air do? It rises. Okay, it's less dense than cold air, so it rises. Cold air comes rushing up, provides fresh oxygen for the fire, and keeps it going. But you go into free fall, and that flow is cut off. So right here, that's the important moment. The flame is starting to extinguish because it's starving for oxygen. The oxygen diffuses in very slowly, and the hot carbon dioxide diffuses outward very slowly. So this has become a very important research tool for us on International Space Station, giving us, if you will, a time microscope to study how combustion works. And let's see. Okay, another example of convective flow turning off. So there's a little oil and water desk toy. They're called executive desk toys because that's how you get your boss to leave you alone. You give him one of those and he plays with it all day instead of bothering you. So here, notice as soon as we go into free fall, the flow stops because that oil is no longer denser than the rest of the oil, the water that it's in. So the flow stops. In fact, there at the moment of impact, you can see that things get disrupted pretty heavily. So that's one of the things on space station is you want to have very smooth ride for the experiments, which means they have to schedule them around the times when the astronauts are going to be on the treadmill, because the vibration will literally resonate, will bump from one end of the space station back to the other, and they can measure it very easily. So, okay, so real quick, this one, those are magnets attached to corks. So the moment I go into free fall, they're repelling, and the middle magnet starts to get centered. And this is actually part of how the sensors in PlayStations and other game controllers work. Okay, so finally this one. Just think about this one for a moment, because we're just about 1 minute out from when we need to start wrapping. What's going to happen to the ping pong ball when it goes into free fall? Any ideas? Okay, and I'm not seeing the chat come up. What's going to happen is it's going to sink. Yep. And there's my 5-minute warning going off. It's going to sink because the molecules, the capillary forces, attraction, same thing that makes the liquid rise, claws on that ping pong ball. It's no longer lighter than the water because everything has no weight. We are in free fall. So these are some of the experiments as such that we do on board International Space Station. And let's go back into Zoom. There we go. And we set this back up real quick. So the instructions, those 2 sets of instructions I give you, you can design and build your own drop tower. I've got this modified so I could have it hang from a pulley out in the garage and do it. If it drops 4 feet, you get 1/2 second of free fall. So you could do science fair experiments with this. I took stuff like this up on a neighbor's plane for students here in Alamogordo middle and high schools so that they could design and build experiments that were in free fall and get an idea of what the astronauts were working on before they talked with one of the space station astronauts a couple of years ago. So I think now we're in the final moments, and I believe, Dave, this is when I'm supposed to take the handful of questions we might be able to get, right?
Yes, you're welcome to take some questions, and you're good if you go a little bit over on this one. We don't have anybody right after, so you're welcome
Oh,
to
cool. Okay.
make it as long as you'd like.
Okay, so yeah, I'm holding it close now, so it's easier to read. And you might, to answer a question, yes, one lens is missing on my readers because after my cataract surgery, focal distances on my eyes wound up different. So it works out fine. So first question. So, okay, let me ask one for you guys, you folks real quick. Why do astronauts get sick in space? What causes that? Why do astronauts get sick in space? Okay, blood. They're yes, they do get homesick after they've been up there for a while. Inner ear problems, that is part of it. They are not used to free fall. Excellent, good answers. What's happening, and NASA does not like to call it space sickness. Oh yes, the blood in their body flows differently, and actually it's not too much gravity. The real answer right now is we don't really know. And if NASA can figure out exactly what causes it and how to predict it, then probably a bunch of people might not get selected as astronaut. Yes, bones too are affected. Okay, so what happens when you go into space? First thing, you get chicken legs and a chipmunk face. Okay, because you think about it, the blood vessels down in your ankles and your legs, lower legs, are really elastic. Think about a tall straw just full of blood, and mechanically, that's what the human body is. So that's a lot of pressure down there. The reason you don't explode and bleed out at the ankles is because those blood vessels are real elastic and they're pressing back. If you don't have the force of gravity causing that pressure head down in your feet, those blood vessels are still squeezing. They squeeze the fluid upstairs. So your legs compress, they get skinnier, and you can actually do this experiment. Just take a photograph, lie down on the floor, legs up against the wall, and have someone take a photograph of your face, and then do it like 5 minutes later, 10 minutes later, half an hour later, and you'll see your face gradually getting puffy. This is why you look puffy in the morning when you get up, is because your body has fluid shifted to your head. One of the studies that NASA does is they put people in bed for several weeks, actually with their feet just slightly up, to try to measure the effects. This may be part of what causes space sickness. The inner ear and the eyes and the stomach all get confused, and the natural reaction can be, ooh, yes. So I mentioned I rode on the NASA Zero-G plane. Did I get sick? Yes, sir. Yes, sir. 3 bags full. And from what I've read, it appears that everybody adapts eventually. Some about a little more than less than half the astronauts will get space sick. It seems like they get really, really sick for just a few hours and then they adapt, or they get moderately sick for 2 or 3 days and then they adapt. Almost like, the total amount of sickness is going to be the same. It's just a question of how much you're going to have. So the inner ear and the eyes have got conflicting signals, and it can cause problems. Some astronauts are never affected. Astronaut John Young, so far as I know, was never affected. Some others, it just does not bother them. Some of them have to take, all the first timers have to take medication when they go up to reduce the effects. So someone said bones. Yes, bones start to demineralize, they deteriorate, because what your body is doing right now is it's tearing your bones apart, but at the same time it's building them up. So this is why walking around is really important, especially for older folks like me. Just exercise, because the little tiny shocks that go through your bones as you're walking, as you're exercising, just doing normal stuff, will stimulate the body to rebuild the bones that get little tiny microfractures. That gives you healthy bones. What happens, unfortunately, with women when they get older is Mother Nature plays a nasty little biological trick on them, and their bones don't rebuild the way they would normally. So they have to take medications like Fosamax and biphosphonates in order to reduce those effects. Astronauts take the same medications. Even the young male astronauts on board International Space Station, who are going to be up there for extended periods, take the same medications that elderly women take in order to stop this bone loss. And this is why it's real important for you right now to build a healthy body. Exercise, get the cardiovascular system in shape, the bones in shape, etc. So you've got a good reserve built, so that when you become a geezer like me, things don't start falling apart. So let me see. Let me open up the chat window. Okay. How does the gravity up in space separate from the gravity here on Earth? Okay, good question. Yes, they do take the meds on orbit. Okay, how does it separate from gravity here on Earth? It does not. Gravitational fields from different bodies will actually merge. So one way to look at it, to think about it, is if you had a big rubber sheet stretched across, well, let's say the trampoline bed, instead of being really, really stiff, was like a giant rubber sheet, and you had a bowling ball sitting in the middle. That's kind of like the gravity field of a planet. So you can roll marbles around, and the marbles or ball bearings like I had here, they're going to put a dent in the fabric also. So the curve from one will match with the curve from another. So in between the two, the gravity field will be a little bit stronger, but then out distant in the other direction, it'll be shallow. But there is still a bit of gravity everywhere. So the molecules, the atoms, the matter in your bodies are pulling on the most distant stars in the universe, and they're pulling on you. Yes, the stars are pulling on you, not enough to make astrology real. Don't, forget that. It's just too random, etc. But that's very real. So let me scroll back here. Blood in the body flows differently. Yes, we talked about that. They're not used to it. May the force be with you. Yes. Gravitational force is always there. But as I said, they're just falling together and never hitting the bottom. And let's see. Okay, what's the average acclimation time on oh, you mean acclimatation? How long it takes them to get acclimated? It's going to vary with the individual. Some astronauts adapt right away. Astronauts going back up, I believe, adapt very quickly, if not instantly, kind of like Owen Garriott. He spent 2 months on Skylab, got his sea legs there, and 10 years later, he was still able to do just fine on board Space Lab 1 and didn't even realize that he had adapted that well. Owen was a really, really neat astronaut. He passed away last year, but he was a great guy. Let's see, too much gravity. We scroll back here. Yeah, the ping pong ball, what that brings up is that forces that exist here on Earth that aren't all that strong suddenly become important in space because the effects caused by gravity are no longer there, or they're greatly reduced. So again, this is why we're doing studies with of combustion and other effects. One of the things that we discovered is that we have to recalculate how the droplets are sprayed into the piston of an engine, because you don't just pour gasoline into a car, it gets sprayed as a mist because all the burning takes place on the exposed surface where the gasoline meets the air. So you want to have a lot of little tiny droplets, kind of like a fog. A lot of gasoline has alcohol added to it. When you burn and alcohol is really, really tough to keep free of water. It's called hygroscopic. It'll soak up water, so getting pure alcohol, even in a laboratory, is really, really tough. But what do you get when you burn alcohol? Carbon dioxide and water vapor. So as soon as you start burning this stuff in the car, in the engine, you're producing water vapor, which is sucked up by the other droplets, and that changes the combustion. So research on space station is letting us see some very subtle effects. And going back to humans, okay, going back to humans, see if can I close this thing or not? There we go. Okay, going back to humans, I mentioned we're just starting to learn the right questions to ask. I'm very fortunate. I got to work as a security guard for Apollo 11, the first manned mission to the moon, when I was in college. They needed extra guards. I saw the ad. They hired me. Had a great time. I was everywhere. I was at the launch pad, the clean room, launch control center, the swamp, with a million mosquitoes that really, really liked me a lot. But overall, it was a great time. We land on the moon, and everybody's thinking, you know what, 10 years from now, maybe 20, we're going to be on Mars again. We still don't have humans on Mars. And now, with what we've learned, really what we've learned about what we need to learn, I'm very grateful that we haven't gone, because I think we would have had a medical disaster with a cruise, that their health would have been debilitated. Some of the things that happen in space, your immune system gets weaker. But at the same time, the germs that we carry get stronger. A lot of subtle effects. You can wind up with little bits of slime mold growing on metal just living off, whatever organic material goes floating through the space station, living off that, and the acid that they produce naturally can etch into the metal and make it weaker. So you wouldn't think of a steel or a metal spaceship as rotting, but that is effectively what's happening. So, any more questions? Appreciate the extra time. No machine. Well, if you have no machines, how are you going to make things work? Yeah, that could be a little difficult. Okay, can we use this info to fly as humans, just us? You mean for humans to fly when they're on board a spaceship or on a low gravity planet? Yeah, there's actually been talk about that if you had a large dome, a large habitat on the moon, it was big enough, humans could build wings, like Wile E. Coyote in the cartoons, build wings and they could fly. Simply because the gravity would be reduced. That's the only way that it would let us do it. We just weigh too much. We're just too big. I mean, you look at Quizlodocodus northropi, the giant pteranodon, I believe it was, from 60 million plus years ago, almost as big as a human, but extremely light body, extremely hollow bones, extremely fragile. Despite its immense size and looking very frightening. So, forget about having something like Rodan in the Godzilla movies. He just is not going to happen. He's just too big. So, any other questions? Yeah, thank you for the compliment. Knowledge base is astounding. I appreciate hearing that. I've just been in the business and loved it for most of my life. Just a space geek since I was a kid. So Dave, I appreciate the time. And again, if you want to build your own, I put the 2 sets of instructions on the page, and you can just download them. They're PDFs, and get in contact with Dave Gibson to have him pass the word on to me, and let me know how you did. Because if things work out great, we'd like to hear that. If they don't, we want to know so we can make it better. Okay, did you go to space because you said you helped with it? No, I wish I could have gone into space. My eyes would not have been good enough to pass the flight physical and so on. Although, if Elon Musk called this afternoon and said, Dave, we want to blast you to the moon, I'd say, what time do you want me at the launch pad? Now, I'd have an argument with my wife about that, but I'd be ready to go. So, and an important note, you don't have to be an astronaut to make the space program work. In fact, we need lots of people who are not astronauts. They have tremendous support systems behind them. Even you wouldn't even think about it, but bookkeepers, people who just track where the money is, where it goes, make sure that the contractors, the companies building all the bits and pieces get paid, and that they've built stuff the right way. Because if you don't build those nuts and bolts just right, spaceships fall apart, and that sort of thing has happened. So it's a tough, demanding business, but it's worth it.